All right, the next type of mirror we want to talk about are spherical mirrors, which we can use to form images that are either larger or smaller. Concave mirror, convex mirror. We're going to talk, typical cheap mirrors are made spherical. In calculus, you probably don't cover it really in most classes, but if you look in the book, they talk about how the real mirrors like this are actually parabolic. Spherical, and they're close, as long as your sphere is big, it doesn't really matter much. They'll both act similar. But we're talking spheres. So I've got a mirror. Here's my curved surface, and this one would be concave, and it has the center of the sphere, center of the circle. So the mirror has associated radius, the center line, and then the vertex is where these two intersect. So in our ray diagrams, we're going to show both of those. Ray path, and my picture's in the way here. You can see that if you come from the center and reflect, as long as you stay close, it'll all come to a point. Actually, if it's a parabola, they'll all come exactly to a point. A sphere kind of blurs it out. I got them in kind of the wrong order. Let me go here. So here's a slide that kind of shows that. We've got multiple rays coming in, all parallel, and they're reflected to a particular point. We're going to call that the focal point. And this one's nice because they use different color rays, and so you can see the white point. That's the focal point. That's what happens when rays come in parallel. Or if they come in through the focal point and hit the mirror, they'll go back out parallel. Now, that's a result of the fact that the law of reflection tells us that the incident angle and the excident angle are equal, but it's on a curved surface, so the way you have to define that is by looking at your tangent planes. But we're going to use we're going to end up with a formula that will let us calculate the image and the object distances, etc. And the way we're going to do that is by, again, a couple of rays. So we're going to use one ray. There's our object. Now remember, we're reflecting, so we don't really go on the other side here. But to get our formulas, here's what we'll do. We'll go from the top of the object into the vertex. That angle and the reflected angle have to be equal, so we draw out a line at the same angle. Then we're going to go through the center, because the center of a sphere reflects back along itself. And you can see that gives us several triangles. Looking at theta, it gives us the big triangle. And then we've got where our reflected rays intersect, which is going to give us the point of our image. Now, that's actual rays crossing. That's going to be a real image. So I could put a screen there and actually form that image. It's going to be smaller, and it's going to be upside down. So it's going to be a magnitude of m will be less than 1, and it'll be negative because it's upside down. Now, if we write the tangent of theta as h over p, and again, we're going to call below the axis negative, so if we take the same angle, it's going to be h prime over q, because remember we said q was the image distance. That's positive. We know that one has to be positive, so we need to put an extra negative on it to take care of the fact that that's upside down. So if I rearrange those, I can get the magnification. If I solve that for h prime over h, I find it depends on p and q. It's minus q over p. You're going to want to use that formula in when we're working our problems. All right. And now, if we look at a different angle, this one that goes through the center line makes us alpha and alpha. Now we've got this triangle, and we've got this smaller triangle. So again, if we write tangent, which is opposite over adjacent, it'll be h over. And now we just want that side. All the way out here is p, object distance. From here to here is r, the center. That's the center. And so h over p minus r, that distance there. And for this little triangle, we're going to have h prime, again negative, and over this distance, which will be the radius minus our q. So we can do a little algebra, rearrange things, and plug in for h prime over h, q over p, multiply, rearrange, simplify, and rearrange, and we get a very simple formula. It's called the mirror equation. Let's get it here on the next page. and it says that 1 over P plus 1 over Q is 2 over R. So that 1 over law that we saw in electricity and magnetism, 1 over P, the object distance, plus 1 over Q, is equal to 2 over R. Now what we're going to do is we're going to call R over 2 our focal distance, because if we were to take our object all the way to infinity, or really, really big, 1 over P, as P goes to infinity, goes to 0, and that means Q, the image distance, is just R over 2. In other words, the parallel rays focus the light at the focal point. So we're going to call that the focal length, R over 2, of a mirror. So what that means is you can take a mirror and take a distant object, and then it will form an image of that distant object at the focal point. And that's a ray diagram for that. So we have the magnification, minus P over Q, and the mirror equation for mirrors. That'll let us calculate, and there's that picture again, that'll let us calculate, if you tell me the object distance and what mirror I have, then I can tell you where the image is going to be and what the magnification is. Focal length for mirrors and half the radius. All right, let's take a look at our simulation here. Here we go. And again, I'll draw some of these, and you'll want to draw them too. So we got a concave mirror here, and it's going to let us move this object back and forth. So pretty far away. There's 3 rays you can use. You only need to do 2 of them. One ray, of course, is to go through the center, because it all reflects along itself, right? Because of the angle 0 coming in, 0 going out. So that's the first ray you can use, and you can use one of the next 2. You can go in parallel, which means you're reflected through the focal point. Remember, the focal point is half the center, so that's half the radius. And where these 2 rays, the blue and this orange one, cross is going to be where your image of the points form, so you know that looks like your image. Or you can go through the focal point and come out parallel. Now, if it's a sphere, they don't quite line up. If it's a parabola, they would line up perfectly. But either one for doing our image. So without doing the numbers, if I did it to scale, I would have the right numbers. But even without doing it to scale, you can tell what? Well, you can tell that your image is smaller. You can tell it's real, because those are real rays forming. And you can tell it's inverted. So you know your magnification is a negative number less than 1. You know your Q is going to be somewhere bigger than R. And as I move, this is, I do a ray diagram, so as I move this, watch what happens to the image. If I come from far away, the image moves out toward the center point until when I hit the center, then that point they cross right close to the center point. And if I keep on going, the image is getting further and further away. These rays are diverging until when I get to the focal point, it disappears. And once I'm past the focal point, same 2 rays through the center, parallel through the focal point, but now these diverge, and you extend them. Your virtual rays actually give you a virtual image back here. I dot them when I'm drawing them by hand, generally. That's a virtual image. So that's a real image. Real rays cross. That's a virtual image. And for a concave mirror, now for parabolic, it's more exact, and you don't really have a center for a parabolic, but the equivalent to the center there. It crosses, but again, you can see they cross more exactly. Well, he won't let me go in on that one. But for the concave, spherical, then we get our virtual image. So the same mirror can give me either a real image depending on where I'm at. Now, if a convex mirror, you'll notice that the curvature is back here. Well, it's kind of quit working. No, there it goes. So I use the same 2 rays, but the center is back here now. So the one that goes through the center reflects along itself. And then the one that comes out, remember, it bounces away. It's a mirror. So I extend it back through the focal point. So these 2 are always diverging, but they cross back here. So for a convex mirror, I'm always going to have a virtual image. Concave can have either. Convex can have both. And then you'll want to look at some of the homework problems. I'll work them out, and I'll do a video showing where I worked them out and showing you the ray diagram. for several of those different cases. There's another nice picture. We usually do this as a demo. You got it coming in. Parallel rays come in, come through the focal point, or if you came out through the focal point, they go out parallel. Ray diagrams, 3 possible rays. We've talked about that. We've got the web assign on spherical mirrors that you can look at. Now here's another one, and there's a nice picture of it. It's inverted. And again, by doing this, I can tell a lot of things about it before I do the numbers to check and see it. Here's where you move in. You can again see what I just showed. Convex mirrors, diverging mirrors, curve out towards you. You always look into them to see the image, and it usually looks further away. It's not inverted. Notice if you go back around the simulation, you'll see it's not inverted. And there's the ray diagram. Again, remember you're reflecting off the mirror, so the first ray that comes in has to bounce, but what direction? Well, as if it's going through the focal point. The virtual ray's dotted here. The center one still goes along the same line. This is one way to remember those. I really do it a little bit different. He focuses on in front or behind the mirror. I don't really do that so much as I just remember that a virtual image has a negative image distance. And there's a summary. All right, now you want to stop. Well, this will be the last of this video. I'll make more on thin lenses, but you want to go work some of the problems and practice the ray diagrams before you go to the next video.